afternoon, everyone. Today's seminar speaker is Roland Arsenault. Roland is a research scientist at data visualization lab here at CCOM. He has a Bachelor of in University of New Brunswick. His specialty is computer graphics, data visualization as it applies to mapping technologies. And today he's going to talk a little bit about his GeoCamera and his mapping.
Thank you. Here. Questions already?
No, the last two seminars I've listened in on the remote hookup, and everybody wants to hear Roland and hear the questions. I think you can pull the microphone down or something to make it better, because it's quite hard to hear if you come in on the remote.
So this far down,
thing. That's it?
Yeah.
Okay.
Maybe you could just stand on the table.
So I should I could do that.
Or wait, a booster seat.
I'll try to project my voice as much as I can. Would that help, maybe?
No, you could. When you're remote, you can hear the speaker, but you can't hear the questions.
So we just need somebody to go out in the crowd with a mic. Okay.
Sorry, Roland.
That's all right. Okay, so I'm going to basically talk to you like you said about the GeoCamera. And first, this is how it works, right? There we go. First thing I'm going to show you is the results, like what most people don't usually do, just so that you have an idea what I'm trying to do here. I'm trying to create maps of the ice. So basically it's about 2 kilometers wide by 5 or 6, kind of looking down on ice. And to do that, using pictures, taken from as high as we can on the ship. So that's the whole idea here. To do that, we developed a system that we call the GeoCamera. And it's a camera that's computer controlled that we can, and then we know where it is and where it's pointing at all times. The purpose that we initially developed for is to create those ice maps, but we could use this in other scenarios. It could be on the ship or other mobile platforms where you might want to take a look at something and know where it is, in addition to taking pictures of it. So here's an example of a GeoCamera. This is the version that we brought on this summer on the Coast Guard cutter Healy. If you notice, that's high up on the LOFCON, which is, on some ships is known as the ice tower. And definitely there's a couple of other cameras you can see there. So that's also a place to put cameras if you want to see around. So where did we get this idea to do this? Colin and I, a couple of years ago, or 3 years ago I think now, we went out with some people from Duke University down to Antarctica to tag whales and to also look at the whole ecosystem, like who else is eating the same food as the whales. So the marine mammal counters, the people, or the observers that were counting all the animals around, they wanted to also have an idea what the ice coverage was to add to their data. So we said, well, why don't we try to build a tool to help you do that? So that's where we started thinking about it. Now, of course, it's not an original idea. Other people have done cameras to measure ice before. Back in '97 in Japan, the Muramoto had this video camera capturing frames at kind of a low resolution by today's standards. And he had it pointing right down in front of the ship, so we definitely got a small area compared to what I'm trying to do. About 180 meters wide, so a bit wider than the ship. It worked, but we need to do a bit better than that for our purposes. Kubo then improved on that and took into account the ship's orientation as the ship would roll and the heading would change, because the previous work didn't take that into account. And he actually did that by looking at 2 frames would overlap and figure out how would that happen. It's because the ship started turning or rolling. So that's how he did it. So you see the idea that we need to not only know where the camera is, but also how the ship's moving when we do this. Then Hall developed an ice cam, which was meant to be basically a package you just bring on the ship, and it'll do slightly higher resolution, still low resolution, but it also did some processing on board to come out with a number which is basically the percentage of ice coverage, and that was the end product. So the fact they were collecting imagery and kind of maybe creating partial maps inside the system, that wasn't their end product. So they didn't try to do something that was wide. They just wanted something that was kind of like a black box that worked. And I think that one they deployed it around Greenland or something. Another version of an ice cam. This one was actually done on the same ship that I was on the Palmer in Antarctica in 2009. Higher resolution, but again, they didn't try to get a wider angle than what's been done before. Still just 140 meter wide swath. And what they did to correct from that picture that looks like a picture from a bridge to a map is I think they set up people with GPS as control points, and then they just did an image warping. And in their paper they said, well, it kind of worked, but it was cumbersome. It wasn't an automated system, and really you should actually do the geometric transformation that we saw earlier that had been done. And that's the approach that I took for what I did here. So yeah, so all the work that we just saw, they were trying to produce the same kind of metrics that you would get from maybe satellite-based radars, and sometimes they would just kind of get numbers like ice coverage or something like that. Well, my approach was, well, let's take the kind of similar approach as we do here for ocean mapping, where we want to create a map, and then from that map we can derive multiple other products from that. So that's one difference in my approach. Oh yeah, like since they're not really worried about trying to get the widest map as possible, in my case, I wanted to match the same survey area, which was about 1 kilometer each side, as the marine observers that were counting the critters out there. So now to get under the hood and talk a bit about the nitty-gritty of how this all works. My background being computer science and computer graphics, I see the word projection, and it means something in that sense. In cartographic world, it means really the same thing, but you kind of think of it differently. So basically, projections is taking the 3D world as we have here, and then mapping it to a 2D surface, which in computer graphics would be your monitor, or in cartography would be your paper map, or if it's an electronic chart, it's built in a computer monitor. So basically, 3D world goes to the 2D screen. Now, the world, the reason I want to mention the computer science and computer graphics side is computer games and 3D movies are popular, and the gaming industry has pushed the development of hardware that allows you to calculate these projections like just really fast. Your graphics cards from NVIDIA, ATI. So that's really cool to know, because we can use that later. So now when I transferred my talk from my computer to this one, it kind of messed up the graphics. So what's basically missing is a box here representing a camera. And here again, we're still going to projections, but kind of in reverse, in a sense where this is our 2D screen, and then we go back and we see our 3D position where this would be our sea surface. And this is in the world of computer vision, which is kind of the inverse of computer graphics. Computer vision is used in robotics, where you want to try to figure out what's going on in the 3D world based on what you're seeing on a camera, which is essentially a 2D sensor. Again, you can apply the projection that we just talked about. In this case, it's actually the perspective projection, because when I talk about projection, it could mean many things, especially photography, it could be locator, whatever. But in the case of computer graphics for 3D world to 2D, so it looks natural, it's the perspective projection. And the same projection is used to model how a camera captures the scene. So I talked a bit about the hardware and computer graphics that does that. One trick that is using computer graphics. Instead of basically just applying the function, you represent the projection as a matrix so that you can then multiply your 3D vector representing a 3D position by it, and then the result is 2D position plus another parameter that could represent your depth on your, basically your coordinates of the pixel on your image. So by using a matrix, there are advantages to that. Again, it's because the hardware they develop is very fast at making those calculations. Now, another companion to the projection is the transformation. So basically, you want to translate or rotate your coordinate systems so that the coordinate system that we're talking about here, which represents the camera's sensor, relative to the ship's coordinate system, which is where the GPS tells you the ship is relative to a certain point, which is usually like down in the bottom of the ship. In this case, a POSM V is just an instance of a motion sensor that integrates GPS and other sensors to tell us where the ship is located and how it's rotated, roll, pitch, heading. And the key thing here is that this tells us where the ship is, but the camera is up there and down. So there's a translation up to it and then a rotation. To kind of give you the parallel of the computer graphics world, if you think of the movie like Toy Story and Woody would be running around the scene, well, the computer scientist that developed that would have him translate, he turns around, would be a rotation. So in the computer graphics world, they decompose these transformations, and then they, again, use a matrix representation to represent them. So if I go back here, and I think that our pixels, which are captured at the camera, which represent these little patches of ice, they get perspectively transformed here, apply a rotation, translation to know where we are relative to the ship. The GPS tells us where we are relative to the world. Therefore, that little patch that I started with, we now know where it would go on a map. So that's how the whole system gets us from a picture to a map. And notice that there are many steps where there are calculations to be made, and those have to be done on every pixel of every image. So that's a lot of calculations. So by representing all these calculations as matrices, there's a trick that we can do, is multiply all these matrices together into one, and you do that once for the whole image, and then each pixel, the vector representing its position, gets multiplied that by a one matrix. So that reduces the amount of calculations the computer has to do, for one thing, plus that those graphics cards that are so popular, they're specialized at doing exactly that very quickly. So there's an advantage to using this approach to doing that. So here's the input image I was talking about. There are some of the numbers that are used to derive all those transformations, and it turns into this. So that's two pictures that explain what I've been trying to tell you in a bunch of vague explanations. If you want any more details on how that works, really just pick up a computer science, computer graphics textbook, and you'll see it'll make more sense of what I'm talking about. Now, how do you pick what camera and how to set it up that you want to use it? Because depending on if you zoom in or zoom out, that determines your field of view. Either you get a wide field of view or narrow field of view. Now, of course, if you zoom in, it's like you're looking through binoculars, you see everything clearly, so that means that you can get a higher resolution for stuff that's far away. But when you do that, you're also getting a narrow field of view. Now, the field of view, that's really dependent on the lens, and then the sensor like, if you've all been shopping for digital cameras, you get your 10 megapixel and 14 megapixel, that's basically the resolution. The higher the resolution means the smaller the pixels are, which allows you to have, again, a higher resolution. So there are many factors that determine what resolution of a map we can create out of a certain configuration. And again, if once we know the field of view and the resolution, now as we go further away from the ship, then everything gets smaller, so that means our footprint gets larger again. So that's another factor that we got to take into account. So I actually put together just a little tool that allowed me to put in all those parameters and give me pictures, like graphics of what I'm capable of doing with a certain configuration. So the camera that I brought on the Healy this summer was basically it's an Axis security camera. It's capable of zooming, and in this case I would zoom from one time zoom to 8 times. So zooming in, as you zoom in, basically you bring your field of view down, and I kind of picked the target resolution of 1 meter. And what that means is once you take your pixel and you project it out on the seafloor, what size is it going to be? Well, not the seafloor. If ever I say seafloor, I actually mean the sea surface. So keep that in mind. That's what happens when you work with a bunch of multiple people. So on the sea surface or the ice surface, the size of the pixel is what I call the footprint, like very similar to the footprint of a sonar. And the further out we go, again, if I use the analogy of a multi-beam sonar, that's like your outer beams where your footprint gets bigger and bigger. And this would be what would happen at if you don't zoom in. So you basically have a wide field of view. Your footprint, by the time we get to 200 meters, we're up to 1 meter. And then, by 500 meters, we're up to 10-meter footprint. Now, by zooming in 8 times, everything comes closer. We don't get to a 1 meter footprint until we get way out to 500 meters. And at a kilometer, we're still at about a 4 meter footprint. So that's where, kind of having a narrow field of view is like, yeah, that's what we got to do. But, if you got a narrow field of view and you want to have the same coverage, it means you have to take a lot more pictures to have the same coverage as wide field of view that we can do it in one. So those are the drawbacks. So now this is just to get our footprint up here. Now here, if we imagine this is the ship right here, our camera is out looking at the side, and again there's 2 ranges. There's kind of the lighter range, which is when we're zoomed in at 1, and the darker red and green when we're zoomed in at 8. Is if we have the camera kind of looking down 3 degrees, where is that field of view? Now, the reason there's a red and green area is if you're on a ship, there is going to be some motion. Now, in the ice, it's not like there's any sea state, but as you're going through the ice, the ship is going to move a little bit, and also sometimes just the balance of the water tanks and such will make the ship move. So I do put in like a 1.5 degree fudge factor, and that's represented by the red sections here. So if you think about a camera looking to the side, just a little bit of motion, now you're looking up at the sky or looking down at the ice. In this, like in a case where you're looking through binoculars, because you got a zoomed in, a small field of view. But if you have the larger field of view, a bit of motion, like we see here, green means that it doesn't matter if we're rolling. So it's yet another thing to keep in mind as we try to select the correct field of view resolution and for the camera that we're going to use. So version 1.0 was developed in response to a need down in Antarctica as we're studying whales and their habitat. This one, we started with a very high resolution camera. It was a digital SLR camera, the nice fancy one where you can change the lens and everything. And we put it on a pan tilt unit, which was a separate component. that was all controlled by a computer. And one issue with it, it was not weatherproof. So basically, the day started, you look outside, oh, it's not snowing, it's not raining, go up, mount everything, and then go sit in the lab and watch and watch. And as soon as you see any sign of rain, snow, anything, got to go and bring it down. It worked. It was a great proof of concept. And so yeah, so here's so there's the digital camera. That's the pan and tilt. All the wires going down to basically the box, and this was way up there. So that's how it was set up. So this is the Antarctic research ship, the Palmer. And those are some of the results that we got from that one. So here you can see where we have a bunch of images. So basically the camera, the pan and tilt allowed the camera to take a bunch of pictures all around 180 degrees and then put them all together into this one map, which, okay, it's not, doesn't look like a square map like you used to see, but it is a map of the ice, georeferenced.
What's the horizontal distance?
Oh, you mean the height?
No, in the image.
Oh, you mean like from the center out to? Yeah, I think I was aiming for about 1 kilometer, so this would be 2 kilometers wide. So if you think that the bow of the ship would be here, but the camera would basically start looking beyond the ship a little bit, you can kind of imagine that the ship would fit in here a bit, so about this size. So now, since those are georeferenced images, what we did is we took a series of them, put them in our software GeoZooey, and put it over some of the bathymetry, and basically this was our track going in this like narrow bay, coming in and out. So we can see we start from areas where there's no ice. You can see that we pretty much have full ice, and maybe there's some leads there, and then we come back out. So yeah, so we got something that worked and made sense. Now, how do we improve on that? First of all, making it weather resistant would be ideal, especially since the cruise in Antarctica, because we were there at a time of the year where it was close to the winter, we only had 4 hours of daylight. So then we took it out for a couple hours, 3 hours, 4 hours, then brought it back in. When we were going up to the Arctic on the Healy, we were going to have 24 hours daylight. I don't want to be sitting 24 hours watching a camera, so I wanted something that could be put out there and didn't have to be constantly looked at. So we decided to just go with a commercial camera that's used for security, which is already designed to go to cold temperatures, can do all the pan and tilt in one unit. So Axis makes those cameras, a network camera. The drawback with a video camera is that we don't get the high resolution as we did from the Canon digital camera, but since we can actually control the zoom on this one, which we could not on the digital camera, it allows us to play that game with the field of view and zooming in that I was talking about earlier, to allow us to get that resolution that's equivalent to what the digital camera would be, but by taking a bunch more pictures. And with the video camera, we could also record a video instead of taking a bunch of still pictures, and then maybe that will help us doing some further processing. Of course, again, I went on a different ship, so the motion sensor is a POS-MV on the Healy, well, I think it was a CPAT on the Antarctic ship, the Palmer. So that means some of the code that interfaces had to be changed. There's a different camera, different system, so there's more software that had to be adjusted for that. So I use the same concept, but there was a lot of rewriting and adjusting the software pack to make it all work. So it was almost starting from scratch, but at least I had the ideas. So this is what it looked like when we just first started seeing a bit of ice, and here's a camera doing its thing. So basically, it will pan side to side. I make it go back looking forward kind of as a reference. And here, I start with the camera kind of like not zoomed in, so it's like at one time zoom. So the field of view is wide. And the first pass that we saw was looking up at the horizon. This one is kind of looking lower. The idea is that there will be overlap, but we get full coverage of what we see ahead of us 180 degrees. Now, once we did that, then let's zoom in. Now we can fill in with higher resolution details. Now, as the field of view is smaller, like I mentioned, the 2 passes I was able to do earlier to get the full coverage now turns into probably 3 or 4 passes. And that would take a while so I won't show you the whole thing. Now, the choppiness that you're seeing, you might think, oh, the computer's slow or something. No, that's just because this video camera was recording 24 hours a day for 40-some days. That's a lot of data. So to try to not collect too much data, I tried to limit it to a terabyte for the cruise. I had the frame rate set at 5 frames per second, so it makes it look choppy. But as you can see, from frame to frame, there's plenty of overlap so that I don't have gaps in my coverage. So, some of the issues we had. Well, the camera was strapped up on the ice tower, as you saw in that earlier image. So I had to figure out exactly where that is relative to the motion sensor, which is somewhere at the bottom of the ship. So that took a few days of work, looking at ship drawings, making measurements. So it kind of took a while to get that right, and I haven't gotten it perfect, so that kind of introduces a bit of error in the whole process. So those are the kind of things that we can work on in the future. The weather, although this is a weatherproof camera, it's got a built-in heater or something, also did come into play sometimes. I'll talk a bit about lighting and the camera adjusting its lighting parameters automatically, which makes it a bit more difficult to blend into a map. And vibrations on the ship, as the ship is going through ice, it shakes and shudders. That actually caused some problems as well. There's the weather issue. Ice would start forming on that cover, and it was the little internal heater was just not enough to melt it. So once in a while I had to climb up there and try to scrape it off. So that kind of caused problems because obviously you can't really get good maps out of that. The exposure, like cameras like to automatically adjust themselves. So if you got maybe the sun over there and you're looking in that direction, it'll darken everything just so that it looks balanced. But then you look at the other direction, lightens everything up. You try to combine that, and you got all these seams. So I had the same problem as well the previous year in Antarctica. So the trick was back then to just say, all right, camera, don't do your automatic thing. I'm going to figure out a value, like the software is going to figure out a value that makes sense across the whole field of view and apply it as a manual setting. And I figured, well, it should work the same here. But the problem with it is that previous movie we saw, the idea was the camera would pan smoothly and I just grabbed frames from that. Well, that auto iris feature in this camera, when you disable it and give it a value, everything would just blur instead of having these sharp frames. So I had to basically have the camera stop, because as you notice when we're panning, everything blurs. So I had to basically stop, and although it's collecting video, just basically take the frames that become sharp when the camera doesn't move and use those as the frames I could use. So this is the stop and go method rather than just taking continuous video. So it's a video camera, but I'm kind of using it a bit like a still camera in a sense. Now, this was an interesting one. You noticed earlier the camera sometimes goes back to this forward-looking position, this home position. I noticed after a while that it seemed that it wasn't always pointing in the same direction. It would kind of seem to drift away. Then somehow the camera would automatically do some kind of recalibration, and then it would work again. Now, that just threw like a wrench through my whole processing, because my idea was, you know where the camera is, it knows where it's pointing and everything. That means the whole pipeline from getting the imagery, combining the navigation, and producing a map should all be automated. There's no room for error. until I found that there was error in my pan and tilt, which basically tells me where the camera's pointing. So that means I had to throw away my automatic processing chain and build a tool that will allow me to handle that. And this, I think, is why I had issues. The vibration that I mentioned made some of the screws come loose. This one just basically came out and it just fell in the bottom of the lens, and the whole thing was kind of hanging. So that's why I could no longer do the pan and tilt correctly. So I think when I found that, then that's when I stopped using this camera for collecting data, and I just worked on the processing of the data that I did collect, and also fixed the issues that were caused by the pan and tilt getting out of calibration. So yeah, that was interesting when we found that. So this is what a user interface that you write quickly while on a ship looks like. It's ugly but effective. It allows me to enter all the numbers, or some of it gets automatically, and then when I see that the results are not quite right, I can go in and just tweak it to see if it'll make it better. So here's a frame that I might want to tweak, and then I can basically say, oh, I want to adjust the yaw, because I think that it might be off by 2 degrees or something like that. And this is where, when you make a change like that, the calculations needed by the computer to do so are immense, and usually it might take a few seconds or maybe a few minutes to calculate that. But if I offload everything to the graphics card, boom, it's instantly done, and I can basically change some parameters and see the results right away. So that's where it was really nice to use the graphics card to help me make those calculations. And let's see here. Just some of the results. So I picked a day that where I knew there was going to be some images available from a radar, a satellite taking radar images overhead. So at about this time, 2 UTC on that date, those are a series of images that I put together. And the reason I mentioned that the satellite imagery is that I would like to get ground truth this to see if I got the georeferencing right. So this is what the actual image would look like. So we're up there, and the satellite goes by maybe once a day, takes an image that shows us the whole ice field for a whole wide area. And then here basically is the location of where the ship was at that time that that image was taken. And so you can see that maybe the individual pixels available are I think something like 70 meters or something like that. So it's quite a coarse resolution to try to see the detail of what's around us. So I use this as kind of like a starting point, something to compare. And when I put my image on it, this is what we get. Now, something to look at. If we look at the shape of this feature here, it kind of looks like this thing right here.
Must be coincidence.
Probably, yeah. Yeah, I think you're right. So yeah, so this is like exciting. Like, you either got it right or it's just coincidence, but who cares? It looks good. So say, all right, let's try it again. So here we have another feature here, and there it is. Now this one, I don't know from you guys, does it look like there is actually an offset? It does, huh? Yeah. This one was taken as the ship was going along the track, maybe 2-3 hours later. Now that image that we saw there from the satellite, that was one image taken when we were back here. So a few hours later, we've moved, the ice has moved, because the ice does flow at a few meters, is it a couple kilometers per hour or something like that, which would actually account for why that now we're seeing this feature here, while before it was there. So that basically means that this feature, in the few hours it took us to get from the other point to here, moved to about here. So either it's a coincidence and we've got a logical explanation for it, or it could just be that I'm wrong. But I think it's the ice flow. That's what I like to think. Here is another example. Again, this one is kind of not as clear to see, but we do still see matching features. Now, you might be wondering, why does this map look like this while the previous one looked like that? This is why. It kind of got foggy out there. So sometimes there are other factors that I can't really control that's got to come into play to prevent me from going out like a kilometer each direction. So, but we can still get some data out of it. Here's just an example of ice that kind of looks different from what we saw earlier. So this is the map that was created, and this is what it looked like looking out the window. So, version 2.5 of the camera, because the one that I took out on the Healy, I called it version 2.0. That screw that fell out, and I said, okay, that's it, I'm not using that camera anymore. Then I still wanted to continue with kind of a different configuration of this project with the existing camera that was already on the ship, one of the ones we saw earlier. So version 2.5 is using the existing camera that's basically a fixed camera looking forward. That one's got a higher resolution, but a wide field of view. So how does that affect what results I'm able to get? Let's take a look. So the wide field of view allows us to basically not have issues with needing to pan and tilt. The high resolution compared to the video camera does allow us to still get our range out to 200 meters away and get a footprint of 1 kilometer with an 89-degree field of view. So if you think about it, that's like 45 degrees each side. That is wide. So that's impressive that we can get, still get pixels 200 meters away. That's with a footprint of 1 meter. But we still can't match what we were able to do by zooming in with the camera, since this is a fixed camera with no zooming. Well, you can manually zoom it, but then once it's set, it's essentially fixed. So the big advantage of that camera is, since it doesn't have any moving parts, it doesn't fall apart like mine did. So it looks like we really would like something like that, but that could do the 1 meter resolution out to 500 like mine did, and 4 meters out to 1,000. So I kind of looked at, if we took that camera, replaced the lens with a narrower field of view, which actually is a zoom lens that can go from 17 to 35 degrees, and we set it to basically the 17 degrees field of view, so we basically zoom that thing in, we can actually go back out to 500 meters and get the same performance with a fixed camera. Nothing that has to be panning and zooming around to get that. So now in this case, it's taking one of those cameras looking out the side, another one looking out the other side, and using the existing one that's looking forward. So 3 fixed cameras replacing one that's kind of looking all over the place. So this is what I would suggest that we would attempt if we were to do it again, which we might. I'm still not sure if that's going to happen, but it's possible that we'll go out and do this again. So basically, we've shown that it can be done. When the weather conditions are good and everything is cooperating, we can get basically 1 kilometer each side, which gives us 2 kilometers, maybe even more of a swath width as we collect our imagery. But we still need to work a bit of the calibration, because kind of some of the things I glaze over is when you look closely, there are still some mismatches the further out you go. And for those of you who are used to the multi-beam world, you know that your outer beams are the ones that are very sensitive to errors in your position and rotation and stuff like of the ship, like basically knowing the correct parameters. So I think we can use that experience in multi-beam and patch test and all that to kind of apply it to this to actually get better quality images. And the fact that if we try it again with fixed cameras, it will simplify the system, so it should make it easier to basically get something that's going to work for the holders. I definitely have to thank a bunch of people from here at UNH, Colin, Larry, they allow me to work on cool stuff like this. The first time we did this was with Duke University, their marine lab. They wanted to go out and tag whales, and added this ice map, so they allow me to do that. But then there's also the techies that work on both ships that help me, put things together. So you definitely got to acknowledge these people as well. I mean, in Antarctica, we were up there 50-knot winds, and we had to re-terminate a cable, which if anybody's, it's like really detailed work out in the cold. And these people, they were able to just go out and do it. Like, yeah, let's do this. This is going to be fun. You definitely got to thank these guys as well. So as I take your questions, I'm just going to show you what else we could do with those pictures that we take. So up in Antarctica, I just kind of created those 180-degree mosaics from those same pictures. So, thank you for listening. And yes.
When you're doing your image manipulation for roll 50,
Yep.
yaw, that stuff, you're also, I assume, doing a adjustment for the advance of the ship as the camera's panning, or are you not doing that?
Yeah, well, yes. Either every image I took or every frame in the video, I would precisely know the time that was taken.
I see.
Therefore, as the ship moved, there'd be a different set of numbers that represents the position of the ship and the rotation of the camera and everything. So at each frame, there is all that calculation that has to be redone.
By using a fixed camera, this is going to eliminate an awful lot of those calculations. Is that not true?
Yeah.
Once
we get the position and orientation of the ship that we get through a motion sensor, probably the rest is all going to be fixed after that. Yeah, it simplifies the problem again. Do you have a question, Jim? Okay, sorry. Yes.
Plan to do 3 cameras, all at 17 degrees?
No.
Or are you going to have the center one at a wider?
The center one, since it's already there, they already take nice pictures of it. I mean, when the helium was up helping mold, we saw a video from the other ship, icebreaking. But they use it for stuff like that. It's out on the website. I don't want to mess with that one. It's the front-looking one. But that's okay, because the front-looking one allows me to the stuff that it's looking at comes at us, so it gets close. So I don't need to get a very high resolution of the stuff that's far away ahead of us. The side ones are the ones that are important because they will look out the sides where we're not going. So we're never going to get close to the phone. The stuff that's ahead of us, we are going to get close. So that's why you set up those narrow ones on the side, but keep the forward one as is.
What I was going to actually suggest was if you were doing a narrow field of view on the front one, to add a second camera to do wide, but you're already keeping it wide.
Yeah, definitely keep it wide.
And how are you correcting for lens aberration, or are you not?
Well, I kind of skipped over that in the talk just because I figured I'm giving you a lot of nitty-gritty stuff about all translations, but I am taking it into account. Yeah. Monica, you had that?
Yeah, well, I mean, this might be moot now if you're not going to use a pan camera again in this, but if you wanted to, could you maybe solve your problem by using kind of, maybe like rubberized kind of shock pads? I mean, that might affect your positioning a bit, but, your yaw and your roll and everything is going to be much lower frequency than all the shuddering when you're in the ice. So if you could, kind of shock pad that to maybe decrease that.
Yeah.
I mean,
I'm sure that would help.
do you think that would just be too risky with them not exactly knowing your...
No, because I mean the vibration does cause these little errors anyways. So even if it was shock mounted, even though that might cause potential error, I don't think. I think it's a little uncertainty that we can't really get around of anyways.
Mm-hmm.
But yeah, it's probably a good solution. Although the simplified solution is even better. Are there other questions? Boss, how are you first?
I'm not sure exactly what the wildlife observers are watching for, but do you ever see things on your camera that they've missed?
I didn't look to see if That happened in Antarctica. The observers that were out there, they were good. They would spot everything. They've done this before. They've got one looking out each side. But I mean, it could be a potential application. Maybe a ship that can't afford to have observers might have a camera doing that, and then later on somebody could go through. I mean, that might be tedious, but it could be used for things like that.
Pattern recognition.
Was that, Dave?
Well, when you showed your image is laid over the satellite image, we all saw the agreement in the big pictures, the big features, I should say.
Yeah.
You had a lot more detail
Oh, yes.
than the satellite, the smaller ones that you didn't mention.
Yes.
So were the ice observers on the ship, not the mammal observers, but the ice observers, were they interested in that part of it? Because that looks pretty valuable, I think.
Well, we didn't have like official experienced ice observers in Antarctica.
Yeah.
But in the Arctic, we actually had the Canadians
Yeah.
had their ice observers, and they thought it is cool, but they're so good at doing what they do already, which is they draw these nice diagrams that show all the ice, and they do a great job. And they said, yeah, this would be a good tool to help us with that. The American ice observers just look at the satellite image and say, well, I think this is what it is. Sometimes they're not quite right. So
McDonald's version,
maybe. Yes.
Roland, I've got one comment and one question. The comment is that the problem that you mentioned of determining the positional offsets and angular misalignments between the IMU frame and the camera frame.
Yep.
In the photogrammetry world, that's called the foresight calibration, kind of similar to a patch test on a ship. There are some automated algorithms for that. I don't know if you've looked into it, but it's something that if you're going to try to do that, you don't necessarily have to reinvent the wheel.
Yeah.
I can point you in the right direction if you're interested.
Yeah, if I would have realized it was going to be a big problem before I was trying to set that up, I would have Googled it and probably found that, but then once you're out there and all of a sudden you don't have Google available anymore.
Well, once you've got the imagery, you can potentially do it after the fact.
Yeah,
It requires
that's
having
actually,
some conjugate image points between overlapping.
That's right, and actually we do have, I think one of the videos we saw the Canadian icebreaker, which was working with us, kind of moving in and out of the scene. So that could be a reference point that we have, because we know its position based on its AIS transmitter telling us where it was every 2 seconds. So I could take that data so that I actually do have points out in my video where I actually know the lat long. So that could help calibrate with that.
So that was the comment. The question is, do you know what types of information people want to get out of this imagery? Have you thought about going to the next step of doing some automated image classification or target detection and try to get?
What we did in Antarctica is once I got those images, one of the guys, Pat Halpin, that was on that cruise, he took it into GIS and then started doing segmentation to be able to classify the different types of ice. So we've already been doing a bit of that. So that's one possibility, and there's definitely others that I'm still kind of trying to make sure that I get this part right before focusing a lot on what else we can do with it. I know there's more questions. Jason?
Yeah, what method do you use to eliminate like the seams between when you actually do the mosaicing, you're pasting the images together? Do you do like a pixel average, or do you just kind of paste them on top of each other?
No, so far my goal is to get all the errors out so that when you actually do put them together, they match. So that's my initial goal. And if I get to a point where I think, all right, this is the best we'll ever be able to do, there's still some seams, then I can apply basically just like kind of alpha blending, a transparency blending just on the error. I mean, I'll look into what the different techniques are at that point, but first I want to see how close can we get before we resort to that. Yes?
The access cameras I've seen in the past, they have some sort of change detection firmware in them so that they can sort of measure the change between frames. Did you consider using that or play with that feature at all?
I saw that it was in there, but I didn't know. Yeah, there are some interesting things because those cameras actually run their own little CPU or Linux and all these little processes which can do a lot of automated things. It's not really specialized for this, but I was thinking a potential implementation would be actually to have the whole software actually running inside the camera itself, which could be interesting. Yes?
Shahak is watching remotely, and he's wondering if
From
you...
where? Okay, just curious.
If you've corrected for the auto gain control of the camera in order not to have dark and bright images within a single mosaic, and then if so, how?
What I would do is basically disable the auto gain thing and just start at some number baseline. And then when I would take one series, I would kind of take the average of the value and then say, oh, that looks a bit dark. So next one, just kind of bump it up and just make sure it stayed within a certain range. So what that meant, that maybe the first set of images might be a bit too dark, but then they kind of go into a range which kind of makes sense and kind of like hover in there. So yeah, so it was kind of like adjust based on what you just saw.
That was done for those images on the screen, wasn't it? Is it? What you were talking about?
Yeah, actually, yeah, the same. Yeah, basically use the same approach using the Canon camera in Antarctica and the Axis one. I think I see a hand in the dark.
Yeah, I was just going to say, I think you wouldn't have to worry as much about gain or iris settings if you're doing feature extraction. So if you're actually segmenting out what areas are ice and what areas are water, it doesn't really matter what the amount is. As long as you have some contrast, you can find the gradient between those areas.
Ah, that's a good point. I guess, yeah, if I'm not trying to get an intermediate map that looks nice, then maybe I don't have to worry about that. So.
And I was wondering for registration between different frames as you're going along, if you were thinking of doing some feature extraction just to do the mapping and the registration.
I was thinking that if I can't get all the translations and parameters right to make the match without doing that, that could be a way to kind of fine-tune the matching. So yeah, that's a good idea. Yes?
Do you think, kind of along the same line of that question, do you think that some of the error that you see is because the ice is actually moving while you're taking pictures of it? I mean, not a lot relative to your speed, but a little and up close, it might make a difference.
That's a good point. And that's like one of the reasons I was kind of trying not to look really, really close to the ship, because that's where obviously you're kind of parting the ice as you go. But it's true that, but I mean, when ice is moving at 2 kilometers per hour, and it takes maybe like 5 minutes to get from here to a few hundred meters, there will be some error. But I think I'm still not at the point where that is my big source of error yet. But it's a good point, though.
Think about etching fiducial marks on the outside of the lens to kind of do image matching. Correct for that motion. I mean, you could see like
well, I don't have to.
marks.
I don't have to.
Here,
the ship itself.
You can see how much the ice is actually moving by doing that.
Well, I think just if I scratch the lens or I look at the ship, it's the same thing. The camera is fixed relative to the ship. Is that what you mean? Like, you can see the bow of the ship and stuff like that.
You can use Canadians as fiducial marks.
Yeah, exactly.
Or polar bears.
Oh, yeah.
It's only if they're recording.
The polar bears are white. I mean, just
But the polar bears are eating the Canadians. And that would be really
Hey,
sorry. Bad comment. It would show up in credits that ice really well.
I'll keep that in mind.
All right, one more. We were talking about Arduinos and sensors, and if you are the sensors available for inexpensive sensors? Are they high enough resolution to actually embed them in the space the camera's in, and then you don't have to deal with all these lever arms and that?
Well,
Because you don't need hundreds of a degree of
I can take my phone that's got my accelerometers and everything, put it up there and not have to worry. But since I happen to be on 2 platforms which happen to be multi-beam ships, the very expensive motion sensor that's already there is going to be way more precise, giving me my positioning data.
How much precision do you need? Do you need that much precision?
Maybe not. You might be right. But since I had that, I wanted to use that for at least to get going. And later on, maybe try it without it. If I wanted to take this on a boat that didn't have the multi-beam with its nice motion sensor, yeah, it's a good idea.
Dan wants you to put this on the coastal surveyor.
We got the motion sensor.
Yes.
What's the order of magnitude cost for the Axis camera-based system?
I think this one was somewhere around $2 or $3 grand for the whole access camera and everything. Now the fixed version of the camera that they're using, I think that one's more like $1,500. So yeah, 3 of those versus one kind of is same ballpark for the price, yes.
All right, well, thank you very much.